On the Origin of Time by Thomas Hurt Ott, Stephen Hawking's Final Theory. What's it about? On the Origin of Time 2023 guides you through the humbling, stranger-than-fiction theories that the late physicist Stephen Hawking developed in the last 2 decades of his life. With quantum physics, holograms, and inspiration from Charles Darwin's evolutionary theory, it reveals what the great scientist came to believe about the origins of the universe. Introduction. What's in it for me? Cutting-edge science that sounds like fiction. The best scientists are those who are open-minded and willing to change their views as new evidence presents itself. This is important because even geniuses can be wrong, just like Stephen Hawking started to believe he was about something very important. In the 1980s, Hawking argued that the rules of physics that govern our universe are immortal and unchanging. But the more he thought about it, the more he began to ask, why does it have to be this way? In this book, we'll cover Hawking's final search for the origins of the rules that control our cosmos. In the process, we'll be diving into some exhilarating, mind-bending ideas that will stretch the limit of how we typically understand the universe. It's going to be a difficult but rewarding ride, so buckle up and get ready to explore the vast complexity of the cosmos. 1. The universe, made for life. On a dazzling summer's day in 1998, a fresh-faced Thomas Hurt Ott crept into the office of the world's greatest living scientist. As a brilliant graduate student in cosmology, the study of the origin of the universe, Hurt Ott was being sized up by Stephen Hawking as a potential protege. Almost completely paralyzed by a rare motor neuron disease, Hawking tapped a clicker with his hand. Gradually, through a computer program and speaker system attached to his wheelchair, synthesized speech emerged. By then, its distinct tone and rhythm had already become permanently associated with Hawking. What Hawking said next laid the foundation for 2 decades of collaboration between the men and the book upon which this current one is based. Hawking told Hurt Ott that the universe seems beautifully, impeccably designed to harbor life, which led to this question. Why did our cosmos turn out to be so sympathetic to us? The further you burrow into the science, the more you realize Hawking had a point. The laws of physics that our universe must obey seem made to order for life to grow. Take gravity. If this fundamental force were just a tiny bit stronger, stars would shine brighter, because the nuclear reactions in their cores rely on compressing hydrogen atoms together to make helium, which gives off light and heat. Greater gravity would intensify this process. You might think that sunnier days on Earth wouldn't be anything to sniff at, until you realize that all stars would exhaust their fuel much more quickly, and life on any planet wouldn't have a chance to develop before its sun withered and died. Also, when the universe was still in its infancy, areas of the cosmos varied slightly in temperature. These variations were only fractions of degrees, but if these had been even marginally bigger, all galaxies would have grown into giant black holes and plunged everything that ever was and would be into eternal darkness. And if these temperature variations had been smaller, no galaxies would have formed at all. Let's take another example. In the hard code of the universe that we were given, protons and neutrons, the things that make up the nucleus of an atom, weigh different amounts. Again, this difference seems trivial. Neutrons weigh just 0.1% more than protons. But if the universe's code had decided it wanted these weights to be the other way around, with protons weighing more than neutrons, all neutrons would have decayed just moments after the Big Bang. That means no atoms, and therefore no planets, no stars, and no people. The Stephen Hawking who wrote A Brief History of Time believed that the laws that underpin our universe are unchanging and timeless. No point asking why, they just are. But as we'll see, he wasn't satisfied with that explanation or any other current explanation, for that matter. 2. Current theories don't cut it. Let's look at how humans have previously tried to explain why the Cosmos Operating Manual seems fine-tuned for life. So far, there have been 2 persuasive views. The first, and oldest, is the belief in some sort of creative designer, a god or gods. They set the rules of the game that the universe and everything in it must follow. A Christian physicist, for example, might believe that God programmed the unbreakable rule that nothing can move faster than the speed of light, something as perfect, intricate and finely balanced as our cosmos must have been designed with life in mind. The second, newer idea is that our universe is one of an infinite number of universes, all living alongside each other, but mutually inaccessible. In short, we exist within a multiverse. Each component member of the multiverse might have completely different laws of physics, and almost all of them would be barren and completely unable to sustain life. But if there's an infinite number of them, once in a while you'll stumble upon a universe that's like Goldilocks porridge. Just right. Neither of these explanations satisfied Stephen Hawking, however, and surprisingly, for the same reason. Let's wind back the clock a bit. In the 20th century, a British-Austrian philosopher named Karl Popper tried to define exactly what science is and what it is not. He came up with a powerful, influential, but devilishly simple formulation. Popper simply said that a proper scientific theory must be falsifiable. That means that it must have the potential to be proven wrong through experiments and evidence. Many people believe in the idea of a creative designer. In fact, it's the most popular explanation for the perfect fit between our universe and life. But it isn't a scientific theory because there's no way of hopping over to the lab, running a few tests, and disproving it. It isn't falsifiable. The multiverse theory suffers from the same problem. How could we ever test whether there are other universes out there? We can't even see all of our own universe, because nothing can travel faster than the speed of light. We are trapped in a pretty big bubble that scientists call the observable universe. There are places in our cosmos where the light given off by stars hasn't had enough time to reach us, so we can't see them. And that light will never reach us because the universe is expanding. It's like we're in a dark field with a lantern and we can't move. We'll never know what's beyond a certain point. Hawking surveyed the territory and was deeply discontent. He realized we needed a new theory of our universe's code. 3. What is the time? We're all used to the idea that we live in a three-dimensional world. Up and down, left and right, forward and back. We shop for groceries, drive cars, climb flights of stairs, and fly 30,000 feet in the air to holiday in sunny locales. But what if we told you there's an extra dimension to our world? A fourth dimension. This extra dimension was found by a man you might have heard of, Albert Einstein. Well, found isn't the right word. The German genius took something present in all our daily lives and something none of us has enough of and mathematically proved that it exists as a dimension alongside our three spatial ones. Einstein reinvented time. Think about it. An object doesn't just exist in a location. It also exists at a point in time. Following so far? Good, because things are about to get weird. In 1983, Hawking put forward something called the no-boundary proposal. Winding the history of the universe right back, he found that time didn't exist before the Big Bang. Everything existed as an infinitely tiny, infinitely dense speck in eternity. According to the no-boundary proposal, there's no point in asking what came before the Big Bang because time didn't exist. But a fraction of a second after the Big Bang, our three dimensions of space emerged. And from these three dimensions, time popped out as a fourth. And this is where the magic of Hawking's new theory, the one at the heart of Hertog's book, starts to happen. As we've seen in A Brief History of Time, Hawking wrote that the laws of physics in our universe were fixed and eternal. But after its publication, he began to change his mind. Instead, Hawking started to think that these laws evolved with the universe in those crucial moments after the Big Bang. Electromagnetism, gravity, dark matter, and the weight of neutrons, these mutated and evolved, just like how Charles Darwin showed us that animal species mutate and evolve. Toward the end of his life, Hawking began to view physics more and more from the perspective of biology. Importantly, these evolutions happened in the quantum realm. This is complicated stuff, but the best way of thinking about quantum physics is in terms of probabilities. The electron that zips around the nucleus of an atom never has a definite location or weight. It only has probabilities of being at a certain place and weighing a certain amount. So, in the quantum kingdom, where everything is a probability, the laws that govern our universe today were hashed out from a range of infinite possibilities. Bizarre, right? 4. Mind-blowing top-down cosmology. If you're scratching your head after that last section, You're not alone. This is profoundly weird stuff, and far removed from our intuitive methods of understanding things in this world seem to be completely disconnected from the logic that governs our daily lives. The only thing to do is smile and marvel at the unfamiliar complexity and magnificence of physics and the universe in which we find ourselves. Try to keep this in mind as we muddle our way through these next two sections. Just now, we said that in quantum physics, nothing has a specific value, only probabilities of being a certain value. But that's not the whole story. Once something is measured or observed, it does have a definite value. Let's go back to our electron. Before it's measured, there's a 30% probability of it being here and a 67% probability of it being there. Once it's measured, though, we know exactly where it is. As well, in quantum physics, there's something called superposition. This is a fancy word for when something has an equal probability of having two different values. Basically, before something is measured, it could technically be in two places at once, fixing a value through measurement and superposition. These two things are important to another mind-bending concept that Hawking and Hertog worked on, one that could revolutionize the study of cosmology altogether. This is called top-down cosmology, and it's easier to understand once we know that bottom-up cosmology studies the universe as it evolves forward in time. Scientists who do bottom-up cosmology start at the Big Bang and go forward, using scientific theories and evidence to predict what we should see. But bottom-up cosmology turns what we know about time, cause, and effect on its head. Remember how in quantum physics, the act of observation fixes specific values? Well, if the universe's laws evolved in the quantum realm shortly after the Big Bang, and now there are human scientists measuring and observing those laws in a strange way, we have fixed them by our observation from a huge range of different possibilities that exist simultaneously as superpositions. In this view, the past becomes dependent on the present, and human observers have a big role to play in this process. 5. Weird science. To complete the tangled, terrifying, yet strangely marvelous collaboration of Hawking and Hertog, we need to explore one final concept: holography. In the last decade, holography has been all the rage in theoretical physics. In this theory, the universe isn't thought of in terms of atoms and space. It's thought of in terms of information. This makes more sense when we realize that in quantum physics, things don't have values like weight or speed, they exist only as probabilities. Now, does everyone remember watching Star Wars, when characters communicate with each other from distant planets? Eerie computer projections of their bodies spring from flat surfaces near the person they want to talk to. This is what a hologram is, a 3D object being projected from a 2D surface. So what does a holographic universe mean? Well, it means that we are living in a world containing 3 spatial dimensions, but that this is just a projection of a universe that contains more dimensions, which we cannot access. What does any of this have to do with thinking about the universe in terms of information? Answering this is about as hard as science can get, but the essential idea is that we have found evidence that our everyday dimensions are holographic from studying black holes. At the center of a black hole is something called a singularity, an infinitely dense, infinitely tiny point. Because it's so heavy, a titanic gravitational field surrounds the singularity in the shape of a sphere. Now, if we think of the universe as being made up of information, it makes sense for this sphere to contain a huge amount of information, right? But when scientists did the math, they found that the information black holes contain isn't equal to their capacity as a sphere, it's equal to their capacity as a circle. What is a sphere represented in 2 dimensions? You got it? A circle. This provides evidence for the holographic universe theory. Hawking and Hertog took this and peered into the beginnings of the universe. They ran some equations and realized that the no-boundary proposal, which argues that the dimension of time was created moments after the Big Bang from the 3 spatial dimensions, fits perfectly with the theory that our universe is a hologram containing higher dimensions. They kept developing this model and incorporated the idea that the universe consists of bits of information. They kept following this back to the Big Bang and realized that as you get closer to the beginning of the universe, you begin to run out of bits, like the resolution of a movie getting progressively grainier until nothing before space and before time. And with that, congratulations, you've made it through our outlandish journey back to the origin of time. Final summary. In the final decades of Stephen Hawking's life, he began to change his mind about how our universe ended up with the laws of physics that govern it. He wasn't happy with previous explanations because they weren't falsifiable scientific theories, and so he went back to the drawing board. He came up with a theory that our universe is a holographic projection that contains other dimensions that we can't access, which helped support his theory that the dimension of time sprang out from our three dimensions of space just after the Big Bang. It was also in these moments just after the Big Bang that Hawking believed our universe's laws changed and evolved on the level of quantum physics, and that scientists today, by observing these laws, have fixed them from a range of infinite possibilities just by observing them.